have to define a system, so then we can define the idea of energy, right? The energy of a system, and then the whole idea of work and what work means and how work affects energy and so on, right? Because they are related. And this is the new concept of this chapter, energy and work. Now, they both are measured in the same units because they are basically related one another. The way they are going to be related is pretty straightforward when it comes to the math, but I want to make sure that it's clear as a concept, right? You probably have seen this before or heard about this also in chemistry when you talk about chemical reactions or even on heat, right? That's when we also bring into the picture the whole idea of work and energy, but that's more thermal energy, right? Here in this chapter, we're going to be talking about a system like what you are seeing right now in front of you, which is a mechanical system, okay, of a collection of masses or objects or particles, and where you have a force exerting an acceleration, and also where we can actually determine the work and how this affects the energy of the system and of the individual objects. So this is a pretty good example. You have the eraser on a horizontal table, and you are exerting a force, right? You are pushing it with a force that is constant, by the way. So that's important. The force doesn't change with time. And you are pushing it, well, it depends, right? It depends how you are exerting the force on the eraser. As you can see on A and B, the force is directed downwards, but there is also a component of the force that will be horizontal. So if the horizontal component can overcome the force of friction, then yes, you can have an object moving and that will produce a work. However, on C, you have a force that is perpendicular to the horizontal, right, to the direction of motion of the object. So in this case, you won't have, I'm going to explain why the concept or the value of work in that case will be 0. So basically it comes from this, right? You're going to have a force acting at some given angle, and we define algebraically the work as you are seeing in the equation there. Okay. So if you remember, right, we define a couple of weeks ago the whole idea of displacement. So you can have a mass on a horizontal table, and as I was showing you with the previous image or picture, right, you can be given a force acting either like this or like this. As you know already, the difference is on the normal. But you know what? Let's just say that mu here is 0. So there's no friction. The definition of work is F dot delta R sine theta. Sine theta is just a number. So what we have here is a dot product of force and displacement. Now, of course, if you are in the horizontal, you can say that the displacement is just on the x-axis, right? So here. So if you remember, displacement and force, they both are vectors. And the angle between these two vectors is theta. So that is when you're going to have again the whole idea of the dot product, right? Because what you have is F dot delta R, in fact, here, well, I can manipulate that, but here actually is just F, the magnitude of F delta R. If I put a vector, I don't need a cosine. And why don't I use a cosine if I just put them as vectors? Because here are the vectors, right? And from dot product, this is the magnitude of the force, the magnitude of the displacement, right? So it will be scalar times the cosine of the angle in between. If you remember, that was the definition of dot product. And in this assignment, chapter 7, you will have questions on dot product. Okay. Now, of course, we are also assuming that the vertical component of the force will not be greater than the weight of the mass, mg, the force of gravity. Because if not, the object will move like this. So we're assuming that, that even though the force is like that, you are pulling the mass horizontally. Sort of like when you pull your luggage on in the airport, right? So what do we have? And then work, the best definition for work is that is a transfer of energy. It's sort of like basically the same definition of heat, but that will be more thermal energy. Work, when you move an object from position A to position B, you are giving that object certain acceleration and speed. By doing that, as we will learn today, you are giving the object energy. Therefore, there is work. The other way around, energy is the ability to do work. That's how they both come together. Now, in the example that you have in there, or you have in front of you, you have a chair that is not moving. You have a balloon on which you are exerting the same force in opposite direction. I can actually add another example. Let's say you lean towards a wall, vertical wall. Or let's say you push it. The wall is not going to move, right? I mean, let's say it's a big wall. So the wall won't move. So if there is no motion, there is no work. You might be exerting some force, but as we know from the definition, work depends on that displacement, right? So there is that. And the force F is the only one that is doing work in that situation that you have in front of you, this one here. That's because the object is only moving horizontally. If you were moving the object upwards, as we will see later with the inclined planes, that is when you will have to also consider the work done on the vertical, or in some cases, the work done by gravity. Now, let's remember that force is a vector, displacement is a vector, so you can technically have a negative force, right? You can. And you can also have negative work, because in the equation that you see in front of you, you have F delta R cosine theta. Now, F and delta R, because they are scalars, they will always be positive, like when we take the magnitude of the work. But a cosine theta, right, can be negative if for angles that are greater than 90 degrees. So let's suppose you have the force on the displacement like this. Probably will see what I mean with this. In this case, the angle is less than 90, right? It's acute. So, and also the force is making the object move to the right, so the work is positive. Remember that A dot B is a dot product. The magnitudes are this and this, which are positive. Cosine theta, however, can be negative. How? Cosine theta can be negative if you have this. Let's suppose I give you the mass, same mass. I'll give you the force. Oh, sorry. The mass is moving some displacement. And the force is like this. Now you may be thinking, that's the angle theta. Not really. You are looking at the angle between the displacement, which is this force. So this vector can be placed here, right? So you're looking at this angle. This angle theta is greater than 90 degrees. Therefore, then, the cosine theta is less than 0. Okay. So now let's understand this physically. We can do this, right? 180 minus theta, so this is F, but because it's so obviously the work see the minus, huh? Okay. If the object is being moved to the left, then we can say that the work is negative. If theta is 0, by the definition of cosine of 0, 1, you have the maximum work. That is when the force is parallel to the displacement. And the units of works, 1 Newton times 1 meter, would be the units of joules. Those are, or that is the unit for work. And later we will see that that's the unit for energy, the joule. We should label it as a capital J. So work is energy transfer. That's basically what we said before, or what I said before. And now let's take a look at this example, or this question here. So every object in the solar system orbits around the sun in almost a circular fashion. The gravitational force exerted by the sun on the earth is radial, right? It's basically a centripetal force. So if you assume the orbit to be perfectly circular, so it's a centripetal force, the work done by the gravitational force during a short interval in time, right, as the Earth moves through the displacement in the orbit, What can you say about the work done by the gravitational force? So that one requires you to, well, think about it. I'm gonna show you guys a picture so you can see what that means. Right? So you have the sun at the center, and you have the Earth orbiting the sun at almost circular fashion. And the thing is that when they tell you that it's in a short period of time, right? You are looking at sort of like this. The thing is that even though the force is like that, that's a gravitational force, by the way, acting towards the center. Even though it's like that, we know from the previous chapter, right, when we did centripetal force and tangential forces, that there is a force also sorry, the velocity is like that, and here is tangential. So you can claim that for a small periods of time, the orbital path of the Earth follows these arrows. And what's the angle between the radius or this force and that velocity arrow vector? It's 90 degrees. So you can say that the Earth orbits the sun with its velocity perpendicular to the gravitational force, which is this. Delta R, then, which is this, is perpendicular. So the displacement and the force are perpendicular. So that means that the cosine of 90, which happens to be there, so the work is 0. The work done by the gravitational force is 0. Which is why when we study planetary motion, we use the conservation of energy and momentum. The energy is conserved if no external forces are making the Earth gain or lose energy as it orbits the sun. And also, we say that the gravitational force is conservative, as we will learn today. Zero. Okay, this one is a mistake. Here they're asking you to rank from most positive to most negative. You want to rank the work. So which one of those possesses the most positive work? Okay. So here is perpendicular. We just said in the example from the whiteboard, when the overall or net force is perpendicular to the displacement, what should be the work? Here, they are in opposite directions, so the angle theta is 180. Here, they are parallel, so the angle theta is 0. Here is making some angle, which is not 180, but still, it's greater than 90. So the most positive work will be which one? The most positive work will certainly be C. F times delta R. This is cosine theta is 0. Oh, 1, sorry, cosine theta is 1. The most negative work, guys, is B. The most positive is this one. This one is the most negative because magnitude-wise, the value of the work is the same as this, but negative. Because the cosine theta here is cosine of 180. Cosine of 180 is minus 1. So that's why. So then, which one is more negative? That's the question that I feel like here they missed in the book. This force is perpendicular to the displacement. So this work will be 0, as we are seeing in the whiteboard. This one, however, in terms of value, right, is less than this and this, but it's also negative, but not as negative as this, because the minimum value of the cosine is when the cosine of the angle is when 180 is when theta is equal to 180. So cosine of theta is minus 1. Here the angle may be 150 or 120. The cosine of 120 is minus 1/2. So it is negative, but not that negative. So positive, very negative, 0, somewhat negative. So the mistake was that positive, 0. Oh, no, wait, that's correct, right? Yeah. Okay, how do we find the work on that example, right? So let's take a look. Remember, all this is with a constant force, huh? We are not dealing with variable force here, which is one of the goals of this chapter. Find the work by any force, not just a constant force. Constant forces are particular situations that we find, but it's not always the case. So you have mass. Let's take a look at the values. So they don't give you the mass, they just tell you that the force is 50 newtons. And the angle is 30 degrees. And it's asking you to calculate the work by displacing or moving the vacuum cleaner 3 meters to the right. Look, let me show you a nice. You can break the force into components. The origin is that it's just moving to the right. So you only care about work horizontally. 50 times the cosine of 30, right? All that. Cosine of 30 is root 3/2. Root 3 over 2 will be 25 root 3 times 3. Joules. Positive because it's going to our right. You can also use a definition if you want. You get the same, right? So that's a simple example. And then, as I was telling you guys in the slides, they go over the definition of dot product, right? So we did this in the first week of classes, right? Because you are doing the multiplication of two vectors, so you have to apply the dot product, right? Or the definition of work is the dot product, right? There are other physical concepts or equations where we will use, as we will see later on, the cross product. So as I did on the first day, basically the dot product comes from the idea of projecting one vector onto the other. That's where the cosine theta comes. Right? That's where the cosine theta appears. Keep in mind that we are not finding the magnitude of the dot product. The dot product is defined by the equation that you have in front of you. So that's why the dot product can be negative, because you're not taking the absolute value of it. And as we know, a negative dot product gives you quite some information about the nature of the vectors and the angle between the vectors, right? Because since you are taking the magnitude of the vectors and multiply by the cosine of the angle in between, the only way you can have a negative work or a negative dot product is if the angle is greater than 90 degrees. So that tells you already what's the orientation of those vectors, right? Is commutative and is associative. You can use it. Just when you are doing the associative, remember that you are dealing with vectors. A dot B plus A dot C. If it's 90 degrees, by definition of cosine of 90 is 0. When theta is equal to 0, you have the maximum dot product AB. And if it's 180, the most negative dot product minus AB. And then, as I explained on the first day of class, first day, right? We introduced the unit vectors for the plane, not just for, I'm sorry, for the space. I, J on the plane, Z on the z-axis, J, K, unit vector K. So the dot product of all those vectors is 0 because they're all perpendicular with each other, right? However, if you are doing the dot product of I and I, J and J, K and K, like here, then that's 1, right? Because the magnitude of the unit vectors is 1. So the magnitude of K is 1. And the cosine here is 0, right? The cosine between K and K is 0. And remember, we can write every vector in terms of the components I, J, and K. Don't worry about memorizing that. That was how we found dot products. Remember? Let's find the scalar product or dot product of that. So let's do all that. Yeah. To find the work. So let's remember, guys. Let's remember that A, for a given vector A, which is, well, that B A dot B minus 2I times I is 1. 2 times 3, 6, is equal to 4. The dot product is, and you can do a lot of things, right? For example, we can find angle between the vectors, magnitude of A, magnitude of B. Now this vector is the first quadrant. This one is in the second quadrant. So the angle should not, or it could be more than 90, but it shouldn't be more than 180. Let's take a look what we get here. Well, the cosine will be, if the dot product is positive, then we can know already that cosine will be positive. If cosine is positive, it has to be acute. Okay, so this one is the square root of 9 plus 4, right? The magnitudes, 4 plus 1. So 4 over the square root of 60. That will make theta approximately 60 degrees. That's what we satisfy here. The 60.3. All right. So we did before. We did that before. So why are we doing this? Because force is a vector, displacement is a vector, so you can have problems like this. They tell you that the displacement given a particle with displacement delta A like that, force meters so we're just gonna find the work. If I just use what I did, that's it. Right? In vector form, this is a dot product. 10 plus 6, 16, scalar. Very simple so far, right? But again, it's a constant force. It's expected to be easy, right? So that's how we find work. And we will do applications of this as well. However, we know realistically speaking, neither force nor many other parameters like, velocity or even acceleration are never constant. or are almost or are hardly ever constant. So how do we find the work done by a variable force? Well, we need to remember our definition of function and partitions. So work for a variable force. So we know force is a force can be what we know a vector field. Okay, so it can also be described as a function that can be given with respect of a variable x. It can be respect to the position or respect of time. Let's suppose that force changes as a function of the position x. So in my plane, in the x and y diagram, on the Cartesian, I can very well have a force that goes from A so this is your f of x. How do I know the total work done by this force from A to B if the force is not constant along the whole displacement? So what you need to know is you need to find the work done by the force in some differential dx. In some distance, the instant, like instantaneous velocity, right? The work is potential work is right. So I can again use my definition of dot product work x initial x final and I get the equation. So then I can define work for a varying force as the integral A to B of F dot. That is the definition of work. The integral definition of work. And that's all given in the slides. Now, of course, if you take the limit, right, that's when you get that equation. But let's remember that when you are integrating f of x dx, you are basically computing the area under the curve. That is the definition of integral. The sum of all the areas. That partition that I made here, I believe there are two methods, right? There is the Simpson rule and the trapezoidal or the trapezoid rule. So, trapezoid. Here I can find the area of this rectangle, and then find, use the lower and upper sides, and you find the work, which, in terms of math, is the area cubed. So this, you can say, is the area under. So you can get a problem, and there is one in the assignment, like the one I'm gonna give right now. I'll show you right now which one. I'm gonna give you a force versus displacement or force versus position graph. And you need to find the work done by the force. And of course, this force will be a variable force, a varying force. So it's a pretty easy example. And by the way, thanks to this definition, we can now start defining concepts of, we can start introducing the concept of energy. As I said, right, work is a transfer of energy. And we are going to start introducing different values for the force. There is one in particular I want to introduce today, which is the one due to a spring, right? The one that is called Hooke's law. Before we go into that, let's do an example of this. Now, depending on the chain, you may not even need to use the integral, just the whole definition of the area under the cube. So we have there a force acting, and the graph versus position is like this. Four goes on. Five. And here is 4. So goes from A, B. So the force is changing as a function of position from 0 to 6 meters. And you want to find the work done during the whole displacement. So you're just looking for the area. Right? So we need to find area. That is a trapezoid. How is the area of a trapezoid? So the work will be the area, scalar, small base, 4 meters. The large base is 6 meters. The height is 5. The area of a trapezoid is small base plus large base divided by 2 times the height. 10 divided by 2, 5 times 5, 25. That is a work done. How easy, right? Especially because the figure is quite simple. Take a look. Can you have negative work? Yes. Let's suppose, and that's what you have in the assignment, right? You have a line that goes like this and then goes below the x-axis. So if you have an area under the x-axis, that area will be negative work. Have something like this. So this is 0 or doesn't that. This area is positive. That's work. So this area here is negative. So you have to subtract. And what about here? You need to build a triangle. That will be the area. This area plus this area minus this area. For example, I have to find out one. Don't forget that this is force versus force in newtons versus. All right. So what's coming now? As you can see, guys,